we're going to get started with the statics problem. My markers are over here. All right, so the problem that I was thinking of, it's for a chair, if you will. Like, you guys have probably seen the like director chair things where you have like some sort of like X-brace. If this thing wrote, that'd be even better. Come on, you can do this. Wow, it's not doing too well over there. Let's try over here. Not doing much better here. So you guys have probably seen a director's chair, something like that, right? With a little bit more solid lines in there. For whatever reason, it's not playing very nicely today. Where that sits on the ground, these hopefully it just kind of gets better as I go and picks up what I'm doing. Wow, that's marginally better. So there's some, at least a little bit more legible. So you have kind of like X-braced legs. You have a seat and all that kind of stuff. We're going to ignore the top half and just kind of focus on the legs for right now. We're going to assume that there's some load on them, like a guy sitting on the chair, and the question would be, can we compute the stress in those legs, and try to figure out try to figure out a factor of safety for them. So instead of starting out with a factor of safety and designing the size of the legs, the question is more of, okay, someone's already made this. We're looking at putting a certain load on it. Will it be safe? And if so, how safe will it be? And an easy measure of that, right, would be like a factor. Wow, this is bad over there. It would be like a factor of safety, because as you have some ultimate or yield strength divided by an allowable stress, or you could also term that allowable stress to be whatever stress you think that it's going to actually see. Wow, this is pretty lousy case. So I have to kind of stay in the bottom left, and it'll work. Okay, so if this sigma allow is the stress that's actually going to be, this is the stress that these members are actually going to see, and sigma u is going to be the ultimate stress or the yield strength, whatever we're going to be comparing that against. If we have a factor of safety less than 1, what does that mean? Not good. Why not good? Closer to 10 would be nice, but what if it was like 2? Would that still be not good?
Depending on what you're defining.
Okay, so what does a factor of safety of 1 mean? Just conceptually speaking, what does factor of safety of 1 mean? Say again?
Factor of safety, if it's like a 1, then it means like you go straight up to the maximum stress allowable.
Right. So if there's a factor of safety at 1, it means that my allowable stress is the same as whatever, or the same as whatever the failure stress is. So that's bad, right? Like, we don't want to design it so that when you hit whatever load you're going towards, the thing blows up. That's a bad day. And if it's less than 1, it means that the stress, the maximum stress you anticipate will be even more than the failure stress. So that's even worse. It means that it will blow up before you even load it the full way. If the factor of safety is greater than 1, you might think, okay, it's now the opposite then. The maximal stress will not reach the failures or stress of the material, and that's what we want. Now, why we make factor of safety so high is to allow for unanticipated loadings. So in civil engineering, and actually to a large extent in environmental and engineering too, it's fairly difficult to predict what the loads will be over the lifetime of the object, because we're talking such a long span, and we can't predict conditions very well. Also, and also there's a limit to our knowledge of how materials work. So, for example, say you guys ever heard of the Tacoma Narrows Bridge? No, it's in Washington State. So it was one of the it was when suspension bridges were new back in the dim ages of the past, right? You guys know what a suspension bridge is? Okay, cool. Okay, so they built and the nice thing about suspension bridges is that your structure doesn't have to be in the roadbed, right? Because it's being suspended by a bunch of cables. A lot of the strength is in that cabling, not in the roadbed itself. So you can make it light. So you can make it a much lighter bridge. It's much easier to make a longer span because the materials use as much materials. The bridge can be lighter. Blah 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 blah. The problem is that when they made this bridge, I mean, on paper it worked great, and in practice it worked great. The problem was where it was located. You had a very strong wind blowing down the valley, and that wind interacted with the structure to cause it to fail. Actually, within I think it was a few weeks or a few months of when it was built. So when we use a factor of safety, we're trying to design for these unforeseen events, the stuff that we don't know, about, or have a difficulty quantifying in an exact way. So in the Tacoma Narrows example, although the actual means of failure are kind of a discussion unto themselves, a way that you could apply factor of safety to that kind of a situation is saying, well, there's this event that might occur if I can approximate a lot of stuff with it because I don't understand it fully. We might get loads up to 8 times what we're seeing. Okay, I'll use a factor of safety of 10. That way we'll be safe. So it's kind of like a fudge. It's kind of like a fudge factor, if you will, in the most precise way of speaking. So anyhow, that's what factor of safety is. Hey, it's getting better with time. Sweet. And in the end, we're always looking for it to be at least greater than 1. If it's less than 1, that's bad. It's about to blow up. If it is 1, it will blow up. If it's greater than 1, we're not doing too bad. So what we're going to look at today with this problem is that we have this chair, rather the legs of this chair, and they're pinned there. They just have like rounded ends touching off the ground, so we can assume that the reactions there are purely vertical. Some load here from the person sitting there. Say it's evenly distributed, so it's half and half. And we're using spruce, say, because spruce is a really nice kind of wood. And for spruce, let's see, 5.6 KSI and 8 KSI. Compression. Okay, spruce has those those ultimate strengths in compression and tension, respectively. Um, I think it's a hardwood, if I remember correctly offhand. I might be wrong with that. So its yield strength is fairly indistinguishable from its ultimate strength. Might think of it as like a brittle material, at least along its long axis. So that's why we're not using yield stress here. And given some dimensions here, so like this is 1 inch. Each leg is the same length. I'm running out of space, which is about 2.5 foot, and the thickness of each leg is a 1/2 inch. And the question is, given a load of, say, 200 pounds, so a person sitting on the chair, weights evenly distributed to these legs, given this sort of a geometry where the legs are pinned together at the center, what is the factor of safety for this design? Yes.
Wait, what do you mean by the width of the chair? Is it not a circle rod?
Correct. They are not circular rods.
They're like square.
They are rectangular prisms. Yeah. So they're like a 1/2 inch thick, inch tall. If I drew a cross section, it'd be something like that, except in more proportion. That'd be like thickness, and then that'd be like, that's H. Okay? So we clear on what the problem is? Cool. So I'm just going to write a couple of values over here. 5.6 KSI, 8.6 KSI, tension, compression. Cool. Question is, factor of safety equals what? All right. Oh yeah, and load is 200 pounds. Okay. So, where do we start? Say again? Labeling forces. All right, so what forces do we have to label? Okay. Okay. Do we have, well, so right now we have a free body diagram of the entire system. On free body diagrams, you only put forces external to that diagram, right? So are there any more external forces on this system? No. Okay. So we have that. If I was to draw, say, like, that was leg 1 and leg 2. Call this leg 1. What would the forces on that guy be? Okay. That would be directed straight up, applied to the bottom left.
Would there be a downward force on the pivot?
Okay, so you have the pivot dead in the center here, we'll say. I'll call it FP Y. How about? Is that the only force there? Okay, because we have that load. So, so we have some load P over 2 floating there. Are there any other forces? So, right, okay. So FPY is the component of that in the vertical direction. At least that's what I inferred from what you were saying, Ian. Is there another component there that we should at least account for? Yeah, it's a pin. Pins can react, have forces in at least 2 directions. So we need to account for that. While we're here, speaking about directions, let's define some that are positive. And we have all this stuff. We have a free body diagram for a leg. We have a free body diagram for the whole system. But like, what are we doing with these? What do we need? What do we need to find? Okay, so we're doing right. We need to start summing forces, summing moments, so that we can determine what all these reactions are, and find out what the internal forces look like. Because if we don't know the internal forces, we can't find stresses. So we need to start defining things. So we need to start somewhere, obviously. So where shall we start? In which diagram? Left. All right, we can start on the left. Come back to this. We'll come back to this guy. Let's write those down somewhere. Oh my. Let's see. H equals 1 inch. Thickness is a 1/2 inch. L leg equals 2.5 foot. Right. Yeah, and 45-degree angles. Cool. All right. So, if I do my sum forces, Y, what do I get?
The reaction vertical force in the bottom equal the D2.
Okay, so we have that guy. Are you saying, should it be that? That is right. You have more forces here, so you can't just state that. So, and this comes from a pin, so it's external to this diagram. So you have to account for it in your summation of forces. So you have FR1, which is going in the positive direction. As you said, we have some load at the top. What else do we have? Right, minus FPY. Anything else? Yep, I don't see anything else. Okay, so that's one summation of forces. But there are 2 unknowns in that, right? So we can't solve it yet. So next step. Yes? Do you guys have a question? Or? Okay, cool. So what's next in this process then? If we can't solve that by itself, what's our second equation? Okay, we can do that. What's the sum of the forces in the X? Any other ones? No, none at all. Actually, slide equals 0. Okay, but that doesn't help us. So that helps us get rid of a force, but it doesn't really help us with solving for some of our unknowns because we haven't, we've added an unknown. We haven't added equations with the same number of unknowns. So what else? So what else can we do? Moments. So stuff. I like it. Where are we taking moments around? What's your favorite place to take moments around? The bottom. Interesting choice, but I'll take it. Okay, so we'll call this point A just so we have a name for stuff. Okay, so what are the moments around point A? Keep in mind, this is a 45-degree angle. So what's contributing to a moment around A? Put it that way.
FBY and B2?
Correct, because FPX is 0. So we know that it doesn't contribute a darn thing. So FPY and P over 2. So the load at the top and the reaction from the pin. So how would I express that? Like, how would I express those as moments? Okay, so length over 2. But does all of FPY create a moment around A? Does the full does the full magnitude? Okay. So if I had, imagine there's a leg for what's called a second. I'm pulling down like this versus like this. Which direction of pull creates a greater moment around the pivot here? This one? The second one, right? Why? No, it's pulling on the same. It's pulling on the same place. More the force is directed perpendicular to a radius from this point. So the direction of the force matters. And if I'm pushing straight down towards the pivot, no matter how hard I push, I'm not going to ever turn this thing. So by consequence, only the component of this force vector that it's oriented perpendicularly to a radius coming from A is going to create a moment. So what's that component? I mean, I know it's the same sine and cosine, but would it be the cosine or the sine, and why? Right. So if I decompose my vector into two parts, so one going that way, one going this way, there's a right angle between those two, and this is the same as this.
Why does it not go like down from like A to F, but down straight down? Like,
I'm not sure what your question is.
so like, you said it was like perpendicular distance, right?
Perpendicular. Yeah, from there to there. Oh, yeah. Oh, I see what you're saying. So if I transfer that to there and measured this distance off, is that kind of what you're saying?
Oh, I thought that FPY would go from FPY down to that line, not like go down past the A line.
Okay. So tell me what it's called. Can you tell me what the moment arm would be for the situation that you're describing?
Like it would be a distance, so like if FPY went straight down, like a distance from A to where they intersect it.
So this?
Yeah.
Okay, cool. Yeah. Okay, yeah, let's call it. You can do that you can do that to too. In which case, yeah, you're absolutely right. Okay, yeah, that makes sense.
But like, is that right if that angle wasn't 45 though, but you said it was sine?
Yeah, I'm actually measuring it a different way. If you do that, goes to there. No, sorry. Be that. Be that or that. Yeah, you end up multiplying different. So here it's that times that. Do that. That's interesting. Never thought about that one before. Oh no, I'm actually back. I'm actually backwards. That would be the angle. So yeah, it would be cosine. Yeah, no matter what. Yeah, you're good. Yeah. Does everyone follow that? It should be cosine
Yeah.
because if I did that trick, or if I just decomposed FPY here, so I try to find these two vectors, the angle here, if theta was 90 degrees, this angle would be 0. If theta was 0, this angle would be 9, would be 9, would be 9, would be 9, would be 90. So that's kind of a indication that if it's cosine down here, it should be sine here because they're varying opposite one another. Does that make sense? Okay. And okay, let's try explaining this a different way. So this, so I can figure out how this angle corresponds to this one based on what this should equal when this is a particular value. So if this pole is straight up, so if it's straight up, that means that FPY be going straight down, right? This angle would be 90 degrees. And this whole little triangle thing here would have collapsed into a line, right? So the angle between the magnitude and the force vector parallel to the leg is now what? 0, right. While this angle is 90 degrees. So they've varied opposite one another. One's gone up, the other's gone down. And if you look at the definition of sine, or the relationship between sine and cosine, sine of theta is, if I make this right, yeah, minus, sine is that minus 90. Right, yeah. Sine is cosine minus pi over 2. So it's called, in the definition of the trig function itself, they each kind of vary opposite one another. They're exactly 90 degrees out of phase. So as sine goes to 1, so say like theta is pi over 2, sine is what? 1. Theta is pi over 2, cosine is 0, right? So these two trig functions are 90 degrees out of phase with each other. So it makes sense that if you have these two things changing opposite of one another, that if I'm trying to find the same quantity by both of them, that my trig function should also be flipped. Does that make sense? Okay, I got at least just one, yes. At any rate, it sounds like we got at least some intuition to it going on. That was more of a I wanted to explain myself a moment. Okay, so getting back to our problem, we have FPY with a moment with an appropriate moment arm, and it is directed in what direction, positive or negative? Negative, right, according to our sign convention. Okay, is that the only thing that is creating the moment around A?
No.
No. What else?
P over 2.
Right. Okay, is it creating a positive or a negative moment, given our sign convention? Negative. So, minus, there's the force, what's the moment arm? And what's the magnitude of the force, but it's not the perpendicular force, so we need that too, and we also need the moment arm. Sounds good to me. L cosine 45 degrees for the same reasons why we add cosine of 45 degrees on the last one. Both those forces are in the same direction, therefore the component should also be, the perpendicular component should also be able to be found by multiplying by the cosine of 45. Are there any other moments? Okay. So what does all this equal? Right. All right. Now this one we can work with, right? Because we only have one unknown in that equation. So if we solve that out, what do we get? Let me make a little bit more space. So you're saying if we solve Py, you have P over 2 on this side, L cosine 45 times 1 over L over 2 cosine 45. So, right, you can put that wherever we want. So that's just moving this over to its own side, dividing by all the L cosine 45 crap. Right. So before we get there, though, if we solve this gets us FPY equals negative P. We agree with that? Okay. Cool. You're on board with that?
Yeah.
Sweet. Okay, so FPY is negative P or negative 200 pounds. What does that tell us about the direction of FPY? Right. Now, for consistency, we're not going to change it on the diagram. We're just going to carry around that negative inside of the number. Cool. So yeah, now we can take this and substitute it back up into here. So if we have that, let's write this over here. FPY equals negative 200 lbs. So if we take that value and substitute it back up into our force balance, we get FR1 minus 200 lbs 2 minus negative 200 pounds force. And from there, we get what? Say again? Say again? No, you don't get 0. Yes. This becomes a positive. 100. Yep. It's not because you move this guy over to the other side. Yep. Or move FR1 over and then multiply by -1. Yeah. So end up getting 100 pounds, which is good, because if we didn't, then the reaction to the ground would actually be pushing into the ground Like the ground wouldn't be pushing up; it would be pushing down. So it's good that this is a so it's good that this is a positive number, because Newton's third law would be having a hard day, otherwise. So cool. We've got FR1, 100 Lvs, FPY. We have the load. So this is everything, right? Do we have to even solve anything on the other leg? Why? Right, because the loading's the same, the angle's the same, everything's the exact same as this leg, it's just mirrored in the other direction. Yes?
If perhaps there were rubber stoppers on the legs
Yes.
to keep the chair from sliding around,
Yes.
would there then be X components of the force?
Yes. Well, there could be, put it that way. If there weren't any side loads, would those rubber stoppers be reacting anything?
No.
Correct. So even though they could, because they could like produce a lot of frictions and that, if there aren't any side loads, they aren't going to have any side loads. So yeah. Okay. So let's clean this all up. Yes.
Okay, wait, I understand that that has to be positive,
Yes.
but negative 200 over 2, negative 100 plus 200.
Yes. Okay. So let's draw this out for one more step. Okay, so you're right, FR1, negative 100 Lvs equals 0. Solve for FR1.
So is it negative 100 plus 200, negative 100, or positive 200?
Oh, sorry. You're correct. Sorry. Yeah. Because I guess I can't do math at 8:30. Well, in that case, FR1 is negative 100. In my interpretation of Newton's laws is wrong. So this is a negative.
I think it's something we use the float as being positive.
Load is being positive.
Yeah, I feel like the load should start out.
It is negative. Let's see. That's negatives. That's pushing up. That makes sense there. That has to be pushing up. Excuse me. Let's see. Let's have a look. So if we do some moments A again, P over 2, it comes down to here, L times, it's negative, as FPY, L over 2 cosine 45 degrees, that equals 0. So if we have FPY, L over 2 cosine 45 degrees equals negative P over 2 L cosine 45 degrees. That goes away, that goes away. You're left with FPY over 2 P over 2. FPY does equal negative P. That part makes sense to me. So that is negative 2. So that is negative 200. Say again? No, because the negative comes from direction. Yeah. It's just magnitude. Yeah, it's just a magnitude. So that's that. and if that's pushing up with 200, that has to be doing that. Oh, that'd probably be why. Yeah, it's because we're not letting it slide. Yeah. Okay. So it's called. So it's called. So it's called. So I think it's only violating in tuition because we're. How do I want to say this? I want to say this because it's called because we're not letting it move. I think that's the problem. But anyhow, it's called let's go. Let's go forward with it for now and get to the important part and get to the important part of the problem. So if we have said that's 0, this is 45 degrees. I'll have a look at it, see if figure out anything in the interim. So in the end, we're trying to get factor of safety, right? So in order to get factor of safety, we have to get stresses. In order to get stresses, we have to get loads. We found loads. So how do we get a stress from a load? P over A. So if we have normal stresses, normal force, get a load. If we have shear stresses, we have a shearing stress. So this would be like a load parallel to a face. This would be like a load perpendicular to a face. So how do we get those internal loads from this free body diagram?
So from point A to where FBY is, that section would be in compression from the forces acting on it.
Well, let's take a section here. So let's like cut it there. Know that FR1 is here. If FR1's there, that means that there's some component of it going that way as well as that way, right? And to balance that, we need some set of loads like that, some internal loads like that. If we're going to sum forces based on the direction that we've written all of these and have them sum to 0, correct? Yes? Okay. So based on that, this is going to be like F between A and P, and this is going to be like our shear force between A and P. Okay, so let's just replace that so that we have some notational difference. So how do I find those? Shear force, just so we have a different letter between it and normal force. How do I find those? The force, it's called to find those forces. Yeah, we're going to have to use those loads somehow. How do I use them?
Well, you take a sine and cosine, and the shearing force and the normal force are equal because of that 45 degree angle.
Right. So I have to decompose FR1 into two components. I know that this angle here is 40. All angles are 45 degrees, really, because that's the angle that this guy's sitting at, which the leg's sitting at. So if I want to get the normal component, make sure I'm saying this correctly. Yeah, because that would go to 90. Yep. I could say to get the FR, say normal equals FR1 sine theta, FR tangential or shear would be FR1 cosine theta. And because I only have two forces in each thing, right? I can do some of the forces normal to the leg and some of the forces perpendicular to the leg, and there'll only be two forces in each, right? There'd be the component of FR1, and there'd be some internal reaction from force. So before I get to FPY, the internal reaction forces are equal to the component of FR1. We cool with that? Okay. And once I have those, I can just plug straight into these equations for normal and shear stress and get whatever the average normal stress and average shear stress are. And I can compare those to the correct choice of ultimate strength and get my factor of safety. Yes.
So what area do we use for the shear stress?
Shear stress is, so you have your cross section, use that area. A shear stress is it just refers to that instead of a force being perpendicular to the cross section, it's tangent to the cross section. We still use the cross sectional area.
So because it's a 45-degree angle, it's the same area, it's the same stress.
Right, so even though the leg is at a 45-degree angle, the internal reaction loads are still perpendicular and normal to the leg. Like I don't have a plane cutting through the leg. Oh, that was weird. At a 45-degree angle, at a 45-degree angle. So I don't have to worry about any of that stuff. If I was looking at a plane like that, then you have like weird cross-sectional areas, right? But I'm not. I'm going straight up with the leg for right now. All right. And you have all that. You get your stresses. You try to find factor of safety. You got to choose this based on what's actually occurring in the leg. Like even though we've drawn it in compression, we've said that by solving for all these forces, that we actually have stuff that's going in. We would actually be in tension right now for this section. So based on this, which is called FR1, is actually pushing or pulling. Pulling. So that means that if I drew that correctly, it'd be going that way. So if I ignore the rest of this and look at just my little section, in order to balance the normal and tangential components of that, those have to be my reaction loads, right? So this section, speaking of its normal full force, is in what? Tension or compression? Tension, right. So that means we have to compare against the tension values. Okay, even though we initially draw it a certain way, you pick these based on what's actually occurring. Okay, and then you can just keep on going up the rest of the leg and keep doing this. Does that make sense? Sweet. Well, that's all I got for the day then.